Okay, can everybody hear me well? All right, great. Right, so I'm broadcasting from Banff today, Banff International Research Station. Okay, so let me see. First, I have a remark to make about. So the previous lecture, I just wanted to correct a point which I wasn't very clear about last time. So we wanted to check that when you look at, say, Euclidean space with the Euclidean distance and a measure e to the minus phi x of all x, and I claimed that this was a CD entropy Kn space if and only if the Hessian of phi plus let's see, minus 1 over capital N minus n gradient phi tensor gradient phi minus k times the identity matrix is non-negative definite. Let's say, so here phi was supposed to be a C2 function. And so hopefully this would be for all x and Rn. So there were a couple of points I wanted to make clearer. So one of them was in the proof, I said, you know, in order to check this condition, we need to examine the convexity of a functional like integral log d mu d volume plus against mu plus, let's say, phi d mu x, the displacement convexity. So let I don't remember what I called it. Hopefully it was ET. Along a D2 geodesic. And I needed to compute the second derivative of E. But a priori, we already know that this functional is a sum of two terms. Let me call them E1 of t plus E2 of t. And so E1 of t is the thing that needs to be convex. The convexity of E1 of t follows from because Rn with the Euclidean metric and the Euclidean volume is itself a CD infinity, zero infinity space. And we knew that already. And we maybe wanted to improve this to CD 0n for finite n. And we also know that this is semi-convex. And it's easy to find the semi-convexity constant. It's something like the C2 norm of phi, maybe times the length squared of the geodesic. Sorry, that's Rn times the length squared of mu0, mu1. And so I a priori know that this thing is semi-convex as a function of t. And then what I'm wanting to check is that I can improve that semi-convexity and then, so somehow what I was trying to show last class is that I can improve to Kn convex under this hypothesis. And so I had this little lemma that said, if you already know a function semi-convex, then its second finite difference quotient is given by an integral of its distributional second derivative. And that allows you to identify, knowing that this function is semi-convex, it allows you to identify the distributional second derivative using Fubini's theorem. So more or less, that's what I did in the last class. Questions about that? And I should also mention that the generalization to Riemannian manifolds says something like a Riemannian manifold with its, and if that's true, and if n is bigger than, well, okay, so it's either this or phi is constant and n is equal to n. There's a generalization of this theorem to Riemannian manifolds, which says that if you put the Riemannian distance and the Riemannian volume, and then you weight this with a density e to the minus phi. In the Riemannian case, this expression gets modified slightly. So you still have this expression, but you have one more term that comes from the ordinary Riemannian Ricci curvature. So this will be in CDEKN if and only if, and again, it's two conditions, either phi equals constant and n equals n, or now it's the Ricci curvature tensor plus the Hessian of phi minus 1 over dimension, parameter minus dimension, gradient phi, tensor gradient phi, minus k times the Riemannian metric is non-negative. And this thing here is sometimes called the, I don't know what it's sometimes called the n Ricci curvature, but it obviously depends on, not only on the parameter n, it also depends on phi. So maybe it should be called the like the n phi Ricci curvature tensor. And I've asked you on the last assignment set to derive a different generalization of this to metric measure spaces. Questions? Okay. And I also introduced in the previous lecture, I introduced the Hausdorff metric and for subsets and the Gromov-Hausdorff metric. And so somehow I wanted to dig deeper into those concepts a little bit. And so recall if XD is a metric space, you can, and then you look at subsets, the Hausdorff metric on subsets of capital X measures the distance between two subsets AB to be basically the smallest R, such that A is contained in an R neighborhood of B and B is contained in an R neighborhood of A. Where by R neighborhood, I just mean a union over all A and A of a ball of radius R around A. And one of the basic features of this Hausdorff metric is that let me recall. So here's proposition 7.33 out of the Ivanov book, and it says that first of all, this DH is a semi-metric, so on all subsets. So in other words, it satisfies the triangle inequality. It's obviously symmetric, and it's easy to check that the difference between a set and its closure, it has distance 0, and it becomes a metric if you you're going to always quotient by this equivalence relation, or which amounts to looking at closed sets. So if I look at two closed sets, then their Hausdorff distance vanishes if and only if A equals B. And so a slightly more interesting proposition is that so in other words, GH metrizes closed sets. So I may denote that by script C in the set of subsets. And so a slightly more interesting proposition is that if the original space is complete, then this set inherits completeness. So CXDH inherits from the original metric space. So if the original metric space is complete, then the set of closed sets in the Hausdorff metric is again complete. And this basically follows by a sort of a clever diagonal argument. Is a clever diagonal argument and the fact that the sum over 1 over 2 to the k is 1 is finite. So let me maybe let me say a bit more. So what does it mean for this to be complete? I.e., if I have a Cauchy sequence of closed sets, I need to identify, I'd like to identify a limit in this Hausdorff distance. And then the claim is that the limiting set, C is the set of all X in the space such that BRX intersects infinitely many Cn for every R positive is the DH limit. And so a remark that I want to make is that because of the previous proposition, I don't need to show that C is closed, because basically if whether or not C is closed, if it's the DH limit of the CNs, then up to something that's Hausdorff distance 0, it agrees with the closure of itself. And since essentially what this proposition says is that when I quotient by identifying any two sets whose Hausdorff distance is 0 to each other, what I get is I'm left with the closed set. So since DH of C bar is 0, we can assume C equals C bar without loss of generality. So I'm already in the set of closed sets. And so how do so then I can just worry about showing that this thing really is the limit in this Hausdorff metric of the sequence of sets. And so to check that, I need to do basically two things. So given any epsilon positive, of course, I know there's a capital N depending on epsilon, such that NM bigger than capital N implies the Hausdorff distance between Cn and Cm is less than epsilon. And then I want to deduce from this something about the Hausdorff distance of one of these guys to C. And so what I need to check, I need to check that for any X in C, and N sufficiently large, the distance between X and Cn is small enough, let's say less than 2 epsilon. And I also need to check that for every N sufficiently large, and x and Cn, the distance between x and c is also less than 2 epsilon. So those would be the two things that I need to check. If I check those two things, then I'm these two things together show that the Hausdorff distance between Cn and c is less than 2 epsilon, and then I'd be done. Oh, right. And so, as I say, one of these is sort of straightforward, and the other one's a sort of diagonal argument. I think the one that's sort of straightforward is the first one. Right. So to see the first guy, I know from the definition of C, by definition, there exists M arbitrarily large with what did I want to say? So I know that this ball of radius epsilon around x, say, intersects Cm. So I know that there is some xm in Cm with dx xm less than epsilon. And on the other hand, by the Cauchy property, because the Hausdorff distance of Cn and Cm is less than epsilon, that implies there's some xn in Cn with distance xn, xm less than epsilon. And then I add these, so by the triangle inequality, I get the distance of x to xn is less than epsilon. In particular, m bigger than the same quantity n is larger n. So one is fairly straightforward, and two is the direction that requires this kind of clever triangle inequality. So so let's see if I can if I get this as well. So right, so for a clever diagonalization argument, so basically I have I can get a sequence of indices for which I'm wrong, it's not a diagonal argument at all. It's only the second point. So maybe it doesn't require a diagonal argument. It's a clever Cauchiness argument based on the fact that you can sum a geometric series. So I'm going to fix x1 to be, n1 to be n. And I'm going to, for larger integers k, I'm going to choose nk larger than nk minus 1, such that the Hausdorff distance between, let's say, CP and CQ is less than epsilon over the 2k if P and Q are bigger than NK. And so I already have, I started out with this point X, which let me call it X1, is in Cn, which is Cn1. And then I'm going to sort of recursively choose xk to be in Cnk such that the distance from the previous guy is less than epsilon over 2 to the k. I guess maybe my indices are off by 1. And I know I can do this. It exists because the Hausdorff distance between Cnk and Cnk minus 1 is less than epsilon over 2 to the k minus 1. And so now the point is that this sequence of points that I've just defined recursively is Cauchy, because as soon as, let's say the distance between, well, you can sum the distances. I don't know what better way to say it. So the distance between xp and xq is less than the sum I goes from, let's say, k to infinity, epsilon over 2I, which is less than epsilon over 2k, as soon as P and Q are both bigger than probably nk or maybe nk plus 1. And so it has a limit. And that's where I use completeness of the underlying space. And obviously by my definition of C, since arbitrarily, these xk's are in the arbitrarily large set ck, this limit has to be in my set C. And so where did we get to? So that tells me the distance of my original guy to C is at most like the sum of this geometric series, which is less than epsilon. In fact, even less than 2 epsilon. Maybe I've lost a factor of 2 somewhere along the way. Okay, so that's basically the proof. And so completeness, so the nice thing about having this completeness is it sort of trivializes the next step, which is this is Ivanov theorem 7.38. That these closed sets under this Gromov-Hausdorff distance inherit compactness from the underlying space. And so we talked yesterday about how once you're in a complete space, a complete metric space, compactness becomes equivalent to total boundedness, which basically means that you can find a finite covering by balls of radius epsilon for any epsilon. And by completeness, so obviously one direction is obvious, but oh yeah, no, there's so by completeness, it's enough to deduce total boundedness. And by completeness of X, we have total boundedness, or by compactness of X, rather. By compactness of X, and that means that for every positive R or epsilon, whatever, there exists a finite epsilon net. X1 to X and in X. And so what I'd like to do is construct from this, now that I know there's this epsilon net, i.e. X is contained in the union of the balls of radius epsilon around the xi. How do you think I'm going to construct an epsilon net in the set of closed sets given by the Hausdorff distance? So I have this underlying space X, given some radius. I know that, say, 10 ball, or I don't know, it's 10 balls of that radius or whatever cover this. Will cover the whole set. I haven't drawn the picture, but maybe I need to add a couple more guys into my net. So if I get that maybe 7 balls of this fixed radius will cover the set. And now I want to move to this huge, much huger space, 2 to the x. Well, maybe not 2 to the x, the closed subsets of 2 to the x. The closed subsets of x, rather. And I want to figure out how can I get a finite approximation in the Hausdorff metric to any closed set, any closed subset of x. Any suggestions?
I might be totally off base here, but could you take like the subsets of the collection of x1 through xn to figure?
Exactly.
Yeah.
So you call this your x, I don't know whether to call it xn or x epsilon maybe, because n here depends on epsilon. And that's exactly right. So you look at 2 to the x epsilon. And of course, the number of guys in here is basically 2 to the n, so it's still finite. And what you need to check is that you then need to check for every closed set in X, there exists a subset such that the Hausdorff distance of X to this subset. No, sorry. Is less than epsilon, I guess. And I think what you may, let me see, I think you probably choose this subset. So C epsilon probably is probably all the points that are within epsilon possibly epsilon over 2. So your C epsilon is basically going to be the set of x in x epsilon such that the distance between x and C is less than epsilon. So it's clear, this clearly implies, so if I take this definition, this clearly implies that x epsilon is going to be in an epsilon neighborhood of C. And to get the other half of this, I need to check that C is contained in an epsilon neighborhood of C epsilon. And I get that because these points cover X. So in fact, every point in X is within epsilon of some point in X epsilon. And so, or is within some point, every, have I got this right? Every point in X is within distance epsilon of one of the xi's. So every point in C is within at distance epsilon of one of the xi's, and that xi will be included in this C epsilon by its definition. So I have this as well. Great. So somehow completeness trivializes compactness. And although I think we're not going to use completeness and compactness in quite the same way at the level of Gromov-Hausdorff, what we are going to use is that when we want to check the Gromov-Hausdorff precompactness theorem, when we want to show that a sequence of metric measure spaces, or in this case, just metric spaces, Gromov-Hausdorff converges, we're going to use this same kind of reduction to checking finite collections of finite points that we used in this compactness proof here. So that, by the way, is Blaschkes theorem, I guess the general Blaschke theorem. And when I first heard about Blaschkes theorem, it was in the context of convex sets. So there's a corollary to this, which is that if I let, I don't know what I should use different letter, right? But I've kind of blown it by, so in fact, convex subsets of Rn, let's say, form a closed subset of C in the Hausdorff metric. This is Euclidean here. And so since the whole set of closed sets is compact for Hausdorff convergence, the set of convex sets being closed is also compact, and that's also sometimes called Blaschkes theorem. And that, so I mean, how to think about Blaschkes theorem is so convex sets, if they're smooth, they're characterized by second derivative being positive of the graph when you write it as of the boundary when you write it as a local graph over the tangent space. Now, of course, C2 convex sets are not closed, but the full set of convex sets is closed, and so it's a natural relaxation, and it's the relaxation you want when you want to get compactness, when you want to be able to extract limits. And I should have, I could also say some philosophy that, so let me say the philosophy since I have it on my mind. So convexity of a function.
Do you need the convex set to be bounded?
Right. Let me think about that for a second. I don't, let me see. Why would I need it to be bounded? I mean, so boundedness helps, but I mean, I'm not sure. Do I need it to be bounded?
I guess C of Rn is not compact if Rn is not bounded, if is not bounded.
Why is it non-compact?
Don't you need the space to be compact, or
Do I need this? Oh yes, inherits compactness. Oh yes, okay, thanks. So I'm sort of struggling with this. I mean, of course, you're right. You're right. I need the space. If for this space to be compact, I need this space. I mean, for this space to be compact, I need this space to be compact. On the other hand, I want to say that even so, somehow Rn is locally compact. So you can write Rn as a union of balls of large radius. And so for every one of those, the subset of closed sets is compact. Now, if I take the union of them, basically what that tells me is that the set of bounded closed sets, not necessarily uniformly bounded, but the set of bounded closed sets is compact. Yeah, maybe you're right. Of any bounded subset of Rn. Now it's still true that I want to say it's still true if I have a sequence of unbounded convex sets. I think I'm pretty sure I can still take a limit. But okay, that's good. That's a nice segue. It's going to be a nice segue into things that we do later when we want to talk about pointed Gromov-Hausdorff convergence. But let's not come to that yet, because ultimately we'd like to have a compactness result for metric spaces which are not a priori bounded or compact. And that somehow I stumbled over this point last class too when I said you have this kind of meta theorem and it becomes a theorem of curvature is positive because that forces the underlying metric measure spaces to become compact. But we want a version. I mean, it's nice to have a version for negative curvatures as well, and then you don't have this boundedness. But so let me see this philosophy that so if I have convexity of a function u on Rn, let's say, it can be checked in two different ways. At least if u is C2, if u is twice continuously differentiable, then the convexity, did I already say this last class? I somehow don't remember. The convexity of u is equivalent to non-negative definites of its Hessian for every x. And if it's not, it's always equivalent. The convexity of u, whether or not it's C2, convexity is always equivalent to, let's just say if u is C0 to make things simpler for ourselves, then it's equivalent to midpoint convexity. I guess I did say something like this. So u of x naught plus x1 being less than 1/2 u of x naught plus 1/2 u of x1 for all x naught x1 in Rn. And so of course this is a more general definition, but it's a little bit harder to check because it's non-local. You need to look at all pairs of points. When you have a function, but it applies in more generality. This is usually when you want to check the convexity of something, you compute two derivatives. It's a nice smooth function. You compute two derivatives. That's local in x. And so somehow this is often the more convenient definition to work with if you're computing things, but this is the more convenient definition to work with if you want to deduce corollaries of convexity, because this one's more sort of robust. This one only survives limits in the strong sense that you would have to converge in the C2 norm. This guy respects limits in the much weaker C0 norm. Something similar is going to happen when we want to look at the CD-CAN conditions. So, you want to start out with, if you want to check it for a particular measure of CD-CAN, then if you're willing to assume something like this, then these are convenient criteria to check. But if you want to see whether CD-CAN survives limits, it's much more useful to have criteria like this guy here. Okay, so now let's move from Hausdorff metric to Gromov-Hausdorff metric. And in order to work with Gromov, so I gave this definition of the Gromov-Hausdorff metric. So recall the Gromov-Hausdorff distance between two metric spaces, let's say M1 D1 and M2 D2. you can think of it as being the infimum of the Hausdorff metric of M1 tilde and M2 tilde over all target spaces Z and D metric with M1 isometrically embedded in Z and M2 isometrically embedded in Z. That's sort of a horrible way to think about it because there's sort of way too many possible target spaces Z, and it's hard to think about what those isometric embeddings might look like. So somehow this is too big to work with. But on the other hand, for any one of these isometric embeddings, in order to define this, all you really care about is how the distance D is behaving on the union of these two sets. It's enough to consider D restricted to M1 union M2. i.e., another way to say that is it's enough to consider metrics, let's say D tilde, on the disjoint union of M1, or not necessarily disjoint, but on the union of M1 cross M2, whose restriction, of course, a metric's always a metric on the product space, such that when I restrict D to M1 cross itself, I get D1, and when I restrict D to M2 cross itself, I get D2, i.e., metric extensions of D1 and D2 to M1 union M2. And that's a little bit more of a tractable thing to think about. And so if I wanted, for example, if I wanted, so now this is, so let's verify a claim. So this is a proposition, again, from Burago, and Ivanov, which is that this Gromov-Hausdorff distance actually satisfies the triangle inequality. That's my short form for the triangle inequality. And so let me sort of illustrate how you would do this. So what do I need to check? I need to check that given metric extensions, so given, let's say, metric spaces x1 d1, x2 d2, and x3 d3, I'd like to check that the distance, the Gromov-Hausdorff distance between the first two is bounded by the sum of the Gromov-Hausdorff distance between the first one and the third one, and the second one and the third one. So, so if d12 is a metric extension of d1 and d2 to x1 union x2, and d23 is a metric extension of d2 and d3 to x2 union x3, I'd like to construct a metric extension of D1 and D3 for which the Hausdorff distance between x1 and x3 is dominated by the Hausdorff distance between x1 and x2 given by this metric extension, and the Hausdorff distance between x2 and x3 given by this metric extension. And then so I'm going to show, what am I going to show? I'm going to show that the Gromov-Hausdorff distance between x1 and x3 is less than the Gromov-Hausdorff distance between x1 and x2 plus the Gromov-Hausdorff distance between x2 and x3. That's what I'm trying to show. And so this distance is defined as an infimum over things like this, and this distance is defined as an infimum over things like this. And so if I can show that for any fixed guys like this that contribute to these infima, I get an upper bound on this, I'll be done. And the way to get this upper bound is you define, I know I want to define D1, 3, and I know that if both of its arguments lie in x1, then it has to agree with D1. So I know how it's supposed to be defined when both its arguments lie in x1. And if both of its arguments lie in x3, it's got to agree with D3, and so I know how to define it. And so all I need to say is, how's it going to look when it's one of its arguments lies in x1 and the other argument lies in D3? So for every x in x1 and z in x3, I'm going to define this, and I need it to be symmetric. So I need it to satisfy this. And then it turns out the good definition is you define it to be an infima over all y in the middle space of D12 xy plus D23 yz. And then you need to check that this the thing that we've defined. There's two things we need to check. We need to check that this thing D13 satisfies the triangle inequality. And there are basically two cases to check. You need to check that D13 of xx prime is less than D13 of xz plus D13 of zx prime for all xx prime in x and z in z. So because of the symmetry of the situation, if I can do this for a pair of points in x and a midpoint in z, I can do it for a pair of points in z and a midpoint in x. And you also need to check that the distance between x and z is less than, say, the distance between x and x prime plus the distance between x prime and z. Again, for all triples. If I can do this for midpoints in x, then by symmetry, I can do it for midpoints in z as well. So I need to check these two things. And these are basically consequences of the definition and the triangle inequality. And it's a good exercise to work them out. I encourage you to work them out. I'm not going to do it here in class. And the other thing you need to check is that the Hausdorff distance with respect to this D13 between x1 and x3 is less than the Hausdorff distance with respect to 1, 2 between x1 and x2, and the Hausdorff distance between 2, 3 of x2 and x3. And if you have this, then since these guys were arbitrary extensions, you can make this quantity as well as close as you like to, this can be made to approximate the Gromov-Hausdorff, the Gromov-Hausdorff distance between x1, x2, and the Gromov-Hausdorff between x1 and x3. And this guy always dominates the Gromov-Hausdorff distance between x1 and x3, so we're done. And so let me think about this for a minute. So we need to check that. And so if I take this metric and I want to show, that x1 is contained in some R neighborhood of x3 for that metric, well, so so sort of if I have x1, it's going to be a series of, I think it's going to, I'm not sure I can make this elegant. I think it's going to be a couple of ugly approximations. So I have this thing here, and I have this thing here, which tells me, for example, so if I call this, my notation is going to get messed up, but if I call this like R1 and R2 and R3, then I know that x1 is contained in an R2 neighborhood of x2, and x2 is contained in an R2 neighborhood of x1, and of course these neighborhoods are defined with respect to d1, 2. And similarly, I know that x1 is contained in, x2 is contained in an R3 neighborhood of x3, and x3 is contained in an R3 neighborhood of x2, where now the neighborhoods are defined with respect to this other distance. And so, for example, if I combine these first two things, I will get, and I want to deduce from the combination of the first two things that x1 is contained in a R2 plus R3 neighborhood of x3, where now the neighborhood is defined using d1, 3. This neighborhood was defined using d2, 3, and this neighborhood was defined using d1, 2. And basically what this containment means is that any point in x1, you can find a point in x2 that's within distance R2 of that point, within this distance of R2 of that point. And similarly, for that point in x2, you can find an point in x3 for which, so i.e., for every x in x1, there exists y in x2 with d1, 2, xy less than R2. And now given y, there exists z in x3, with d2, 3 of yz less than R3. And since d1, 3 was defined using an infimum, that y contributes. And so the sum of these two terms dominates d1, 3, and therefore what I get is that d1, 3 of xz is less than R2 plus R3. By the definition of d1, 3. So that's somehow the flavor of how it works. Other questions? And you have to, so I checked one direction, but you have to check the other direction as well, but it's pretty clear that it works by symmetry. Okay, so that's nice enough. There's another way of thinking about Gromov-Hausdorff distance, which is through what are called correspondences. So we say a subset R of the product space is called a correspondence. It's the simplest definition in the world. If and only if basically for every xy in the product space, there exists x prime and y prime in the product space such that x is related to y prime and x prime is related to y. So in other words, the projection of R onto both x and y is onto. Maybe I should call this, I could also have called that the projection onto the first factor of R, and the projection onto the second factor of R covers Y. And you can define the distortion of a correspondence basically measures how much distances change. So it's like the supremum over all pairs of points, x, y in R and x prime, y prime in R of, you want to know if you look at the distance between x and its partner, how different is that from the distance between y and its partner when the partnership is with respect to the correspondence. And then, so here's another theorem, also from Barago, and Ivanov. And it gives an intrinsic characterization of the Gromov-Hausdorff distance. So somehow I defined the Gromov-Hausdorff distance in an extrinsic way. I said you have to define the two, you have to embed the two metric spaces isometrically into a bigger space and then look at the distance in the bigger space. So that's somehow like what do you call it? Extrinsic curvatures, when you talk about embeddings of manifolds in some ambient space like Rn, and the mean curvature measures how the submanifold curves inside the bigger space. There's also an intrinsic characterization of the Gromov-Hausdorff distance in terms of correspondences. And it basically says that for any two metric spaces, the Gromov-Hausdorff distance between them is up to a factor of 2. The minimal distortion among all correspondences. The product. So we look at correspondences whose projections cover x and y, and the correspondences are sets of pairs of points. And if we try to choose the correspondence to minimize how different the distance of x and y is from the distance of the partner, the distance of x and x prime is in x from the distance of the partner points in y. So maybe to make this clearer, I should have called this the x distance of x and x prime and the y distance of y and y prime. And minimizing that distance up to this factor 2 gives you the Gromov-Hausdorff distance between the two spaces. And sort of one direction of this equivalence is fairly straightforward, and the other direction is rather trickier. So let me give a proof sketch. So proof. First, suppose if I'm gonna, so step 1 is assume the Gromov-Hausdorff distance is small. So let me call this 1/2 I, where I is the infimum. And it's not that hard to prove then that I is less than 2r. And so basically, you assume the Gromov-Hausdorff distance is small, and you need to define some relation which gives you this upper bound that you want on r, i.e., so there exists some z with x and y subsets of z, isometric embeddings, such that the ordinary Hausdorff distance, or the Hausdorff distance with respect to dz, my notation is lousy. I don't know where to put the dz. Let's say the Hausdorff distance of x and y is less than r. And so now you define the relation to be the set of all xy in x cross y, such that the z distance between x and y is less than r. And then you try to compute the distortion of this. So first of all, so why is this a relation? So, or why is this a correspondence? R is a correspondence. So in other words, this projection covers either factor. And distortion of R is less than 2R. And if I can do that, I'm done for this, for concluding this. Actually, this is enough. So it's a correspondence because whenever I take any point in X, because of the Hausdorff distance tells me I can find a Y in Y such that dz of xy is less than R. And so that tells me that the projection of R onto the first factor covers X. And by symmetry, the projection onto the second factor covers X. And then to check the distortion, you're basically wanting to, it's the supremum of it's the sup over pairs of points again. But I claim, so of course the restriction of dz is dx. So I could have called, this could have been, you know, I can think of all of these things as being distances in z, because this is a metric extension of both x and y. And then I claim, using the triangle inequality in z, that this is less than the distance from x to y plus the distance from x prime to y prime, right? And you have to check it for both the positive and negative thing of the thing under the absolute values. But for example, the distance between x and x prime is less than the distance xy plus the distance y prime plus the distance y prime x prime. So that's one use of the triangle inequality. So use the triangle inequality in z twice for each sign of the absolute value. And this distance is less than r by definition, and this distance, because these things are both in the relation, in the correspondence rather, this distance is less than r and that distance is less than r, so this is less than 2r. And that's the end of this direction. That's somehow the easier direction. The harder direction, I'm going to plug my grid. Conversely, given correspondence, with distortion less than 2r, I need to construct a metric extension d of dx and dy to x union y such that the Gromov-Hausdorff distance of, or the Hausdorff distance of x and y with respect to this extension is less than r, or equal to r would be fine. And then the claim is that again, I know how, so d, I need to define d as a function of two arguments, but if both arguments in x are at x, it's given by this, and if both arguments are in y, it's given by that. And so I only need to define it for one argument in x and the other argument in y, and of course I want the definition to be symmetric. And the claim is the definition that works is this one. It's the infimum over all points in the relation, the correspondence rather, of the distance xx prime plus r plus the distance y prime y. And again, there are two things to check. One of them is, i.e. d satisfies the triangle inequality, which is actually pretty tricky to check. And I'm gonna not do it in class. And then the other thing to check is that you really get this bound that we want. And that's sort of easy to check. So, so observe, so that's, let's say, homework. And that the Hausdorff distance between x and y then for this d is less than r. And that one I hope is easier to check because if I take some x, any x tilde y tilde in r, and I want to look at what is dx tilde y tilde, then I can just choose the x prime over here, y prime, to agree with x tilde y tilde, so that these two terms drop out and that this is automatically less than r. And so therefore x is contained in an r neighborhood of y, and y is contained in an r neighborhood of x, where the neighborhoods are constructed with respect to this metric we just defined. And so that gives this thing that we wanted. So modulo checking that, but more or less, so I mean, somehow when you're wanting to define distance, the moral of this story is that when you're wanting to define distances, taking infima are a helpful thing to do. And we saw that already in this previous proof. Although, sorry, not that one. Well, yes, there's an infima there, but I deferred another thing to homework as well, which is much easier to do. And it was to check that when you define D13 using this infima over midpoints, it satisfies the triangle inequality. So somehow these constructions using infima cooperate very nicely with the triangle inequality. All right. And then, so there's, so here's an annoying. So what I basically like to do, I'd like to use, so what's useful about this business about correspondences, apart from that it gives us intrinsic characterization of the Gromov-Hausdorff distance. So I'd like to prove a theorem. But I need there's a hitch. There's always a hitch. So in order to prove the theorem, I need a couple more definitions, but maybe I state the theorem and then I'll give the definitions. So the theorem I'd like to prove, which is that for every pair of compact metric spaces, DGH is bigger than 0 with equality if and only if they're isometric. So just as the Hausdorff distance gave an honest metric on closed subsets of some given space, the Gromov-Hausdorff distance gives an honest metric on metric spaces up to isometry classes of metric spaces. And so I claim that the characterization in terms of relations is more convenient for showing this than the characterization in terms of than the original definition of the Gromov-Hausdorff distance. But in fact, you need something that's even a little finer than the characterization in terms of relations. So let me, but it comes from the characterization in terms of relations. So let me pull it up. This is one more way of thinking about Gromov-Hausdorff limits. So here's yet another definition. A possibly discontinuous map F between metric spaces is called an R isometry if two conditions hold, or an epsilon isometry. So it's an approximate isometry if and only if, first of all, the distortion of the graph of F is less than epsilon, and secondly, the image of X under F is an epsilon net in Y. So in other words, epsilon, if you cover the image of X with epsilon balls in Y, you'll get all of Y. And the point of this definition, or the convenience of this definition, is that so it's a corollary of the preceding theorem. If the Gromov-Hausdorff distance between two spaces is small, let's say less than epsilon, then there exists a 2 epsilon isometry between the spaces. And conversely, if there's an epsilon isometry, between X and Y, then the Gromov-Hausdorff distance is small. And both of these things basically follow from the come on, there we go. Both of these facts basically follow from the preceding theorem. So, well, okay, so let me do the proof because it's cute. So basically, so the first direction would be that if the Gromov-Hausdorff distance is less than epsilon, our theorem, we just saw that there's a correspondence with distortion 2 epsilon. That was the theorem. Sorry, let's say strictly, make them both strict. And so I'd like to turn this correspondence into a mapping from X to Y. And so for every X in X, because the definition of a correspondence was that there exists a Y in Y such that XY is in R. So I'm going to set f of X to be Y. And notice that I think that I just use the axiom of choice because I want, if X is an uncountable space, then I need the axiom of choice to pick a Y from each. I can look at all possible Ys that correspond to a given X. I need to choose one of them. And then I claim that this F that I just defined gives an epsilon isometry. Or a two epsilon isometry. Oh, no, hang on. So a two epsilon isometry. So clearly, because of this, obviously, graph of F has distortion less than 2 epsilon because its graph of F is a subset of R. And so the other thing that I need to know is that I cover that the image of capital X under F gets within 2 epsilon of every point in Y. Also, given any point in Y, because R is a correspondence, there exists an X in X with XY in the relation, the correspondence. And right. But somehow, wait, f of X could be far from, I need to somehow use, yes, right. Also X f of X is in the relation. So the distance between XY, the distance XX minus the distance Y f of X. Let me erase something. Get rid of this. Let me get rid of that. The distance Y f of X has to be less than the distortion of R, which is less than 2 epsilon. And obviously this is 0. So f of X has to be within 2 epsilon of Y. So that's the second property I needed for an epsilon isometry, namely this one here. And finally, the other way around, if I have, so conversely, given a 2 epsilon isometry, given an epsilon isometry, yes. Given an epsilon isometry F, I need to define a relation. So what's the relation going to be? It's going to be the set of all XY in the product space such that the distance between of y rather to fx is less than epsilon. And I claim that that defines a correspondence and with this a correspondence with distortion of r less than 3 hats epsilon. And if that's the case, then by the preceding theorem, I'm done. The distortion was basically proportional to the Gromov-Hausdorff distance. I'm a little worried that, oh yes, that the distortion that bounds 2 times the Gromov-Hausdorff distance. So I'll be done. Maybe I guess I can tolerate a slightly worse coefficient. But so let's check about this correspondence. So it's clear. So what does it mean to be an epsilon isometry? It means that the distortion of the graph of f is less than epsilon, and basically the graph of f is this relation. So that part's good. And then the other thing that I need is that the oh no, sorry, this isn't quite the graph of f, because I didn't insist. If I insisted that this distance be 0, then I would be writing the graph of f. So I have that the distortion of graph of f is small, but now I'm perturbing this by, so the distortion of the relation is the sup over all xy in R and x prime y prime in R of the change in x minus the change in y and so this is like, so this is something like, for xy to be in the relation, I know that the distance, I know that this is the distance between x and x prime is less than the distance x to f of x plus epsilon. And for this guy to be in the relation, I know that the distance between y and y prime is less than the distance y to fy plus epsilon. And because I'm dealing with an epsilon isometry, I know that this distance here right, I know that the difference, so this whole thing is less than 2 epsilon plus dx fx minus dy fy, and that's less than 3 epsilon. So in fact, what I got is the distortion is less than 3 epsilon, but the distortion controls 2 times the Gromov-Hausdorff distance. The Gromov-Hausdorff distance is less than or equal to 3 adds epsilon. Phew, that was what we wanted. Okay, so basically so with these extra definitions, I'll start next class by proving that the theorem that I advertised. And I will continue next class by proving the Gromov-Hausdorff precompactness theorem, which says, that if I have any class of compact metric spaces and they're all totally bounded and uniformly so, so in other words, given an epsilon, I have some large number of points such that every metric space in this class has a net with no more than that number of points, then I can find a Gromov-Hausdorff convergence subsequence. And I'm actually going to construct the Gromov-Hausdorff limit explicitly, so I won't need completeness in order to deduce that the Cauchy subsequence has a limit. So that's the agenda for next class. Other questions, problems, or difficulties? If not, I'm going to stop the recording and transition to office hours.